In this portion, I'm demonstrating freefall. On the left, the ball leaves my hand with no initial velocity and is accelerated toward the ground by the force of gravity. Once the ball reaches the ground, it bounces a few times, each bounce smaller in height than the last until it stops. Freefall is only the part from when the ball leaves my hand until the moment before it hits the ground. That's the part we'll be considering when we talk about freefall. The post-impact bounce and spinning of the ball is interesting, and it still follows energy conservation, which we'll use to solve the part that's freefall, but we'll talk about bouncing and spinning more in depth later. On the right, you can see the ball's trajectory, and each point is taken at an equidistant piece in time. So if it's the same number of seconds between the first point and the second point as it is between the 10th point and the 11th point, always the same time step. The points are close together at the top, which indicate that the ball is moving slowly, as in it starts from 0 and is accelerated, which means its velocity is increasing. It's accelerated toward the ground by gravity. The points get further apart as the ball reaches the ground, which indicates that it's speeding up. We can use energy conservation to solve for this final velocity right before it impacts the ground. We have here a word problem typical from a physics book that describes pretty much what we saw in the last video, that a soccer ball falls from rest. This time it's from a ledge 10 meters high instead of a balcony. And we're asked, what is the magnitude of the velocity of the ball just before it hits the ground? So the ball will start from rest, which means we know that the initial velocity equals 0 meters per second. And because it's on Earth, it is accelerated by gravity toward the Earth. Gravity equals 9.8 meters per second squared. The ball will continue getting faster and faster until it's at its fastest, the final velocity, right before it hits the ground. And that's what we're going to be looking for in this problem. I'm going to use the text and I'm going to highlight these things, and we can use them to figure out how to solve this problem. We know from reading the text that the soccer ball falls from rest. That means that the initial velocity is 0. And we represent the initial velocity as v sub I. And just like I showed on the figure, it equals 0 meters per second. The next thing we learn is that the ledge is 10 meters high. That means that the initial height h sub I equals 10 meters. We also learn that we would like to know the velocity of the ball just before it hits the ground. Before it hits the ground, that's right here. We call that h sub f, meaning the final height, and is essentially 0 meters. And what we're asked to find is the velocity of the ball at that point. So we're asked to find the velocity of the ball right before it hits the ground. And that is our final velocity. We have an initial and a final velocity and an initial and a final height. This lends itself to using energy conservation to solve. Energy conservation for the sort of problem we're talking about would be to be looking at the initial potential and, it would be to look at the initial gravitational potential energy, which is your energy of height, and the initial kinetic energy, and look at how those change into the sum of the final kinetic and final gravitational potential energies. So we're going to use energy conservation and that will be the kinetic energy plus the gravitational potential energy equals, in the initial state, the kinetic energy in the final state plus the gravitational potential energy in the final state. And those equal 1/2 mv sub I squared plus mg h sub I. So that's the initial energy of movement and the initial energy of position above Earth's surface. And that equals the final energy of movement plus the final energy of position above the Earth's surface. All right, so this is the final kinetic energy and the final potential energy. So we have 4 terms, and in each of these 4 terms, there's a mass. And we can cancel the mass out of every term. When we do that, it's like saying that the final solution to this problem will be independent of mass. Right? So it doesn't matter whether you have a bowling ball or a feather or a golf ball. They're all going to be accelerated by gravity the same amount. Now, you live on Earth and you deal with reality every day, that's feathers do not fall at the same rate the bowling balls fall. And that's true. In physics, we solve problems by being really specific about what we're solving. And in the case of energy conservation, I'm only going to look at the kinetic energy and the gravitational potential energy. I'm not going to assume that there's any air resistance. Right? There's no energy loss to heat or wind. So but we're very specific. Every time you solve one of these problems, you're going to be in a situation where you can neglect air resistance, you can neglect wind. It happens through the math that the final state is independent of the mass. It's also very important to write down your knowns and your unknowns. So we know that the v sub I, which is the initial velocity, that equals 0 meters per second. We know that h sub I, which is the initial height, is 10 meters. We know that h sub f equals 0 meters. And our unknown are v sub f. We don't know what that is. We've been asked to find it. Now, as a piece of information that's good for problem solving, we notice that we have 1, 2, 3 knowns and 1 unknown. And in our energy conservation equation, we have 1, 2, 3, 4 terms. And we have 1 equation. So we have 1 unknown and 1 equation. There are 4 unknowns in that equation. If we want to be able to solve this with 1 equation, we can only have 1 unknown. So 1 equation, 1 unknown. We should be able to solve it. I'm going to rewrite our energy conservation equation at the top of this page. And that is, remember that the initial kinetic energy, 1/2 mv I squared, plus the initial gravitational potential energy, mg h sub I, equals the final kinetic energy, 2 mv sub f squared, plus the final gravitational potential energy, mg h sub f. And we were able to cancel all of the masses, and this was independent of mass. We can see from the list of knowns that our initial velocity, and our final height are both equal to 0, which means that this term is equal to 0 and this term is equal to 0, which leaves us with just two terms left. I'm going to rewrite these as g h sub I equals 1/2 v sub f squared. So right now, we see that we have this is our unknown, and this here is a known. And the 1/2 and the g are constants. It's customary to put the unknown on the left side, so I'm going to rewrite this equation. All right, and now I'm going to isolate v sub f by moving the 1/2 over to the other side, by multiplying both sides of the equation by 2, and taking the square root. So we have v sub f equals the square root of 2 times g times h sub I. So what we've learned is that free fall from rest gives us a final velocity that depends only on initial height. So if we want to get a number for this, we need to substitute in the values we found on our knowns. So substituting in, we find that v sub f equals the square root of 2 times 9.8 times 10. We can't forget the units. Those are no units for 2, 9. We can't forget the units. We have no units for 2. We have meters per second squared as the units for gravity, and meters as the units for the height. And this equals 10 times 98 times 9.8 is 98, times 2 is 196, so we're taking the square root of that. And meters times meters is meters squared divided by second squared. So v sub f equals, the square root of 196 is 14, and the square root of meter squared per second squared is actually meters per second. And that's great news because meters per second are the correct units for velocity. So we've got a good answer for the velocity. So any ball, feather, weight falling from a height of 10 meters should reach a final velocity of 14 meters per second right before it hits the ground.